Now, we come to the next section where we will discuss what we call Arzela-Ascoli Theorem and the equicontinuity. Now, you see, we have seen in the course of reanalysis, and not only this, we have also seen in the chapter of compact spaces that a compact subset of Rn, every compact subset in Rn, or not only in Rn, but every compact subset in finite dimensional space is closed and bounded. So, every subset in Rn is closed and bounded and vice versa. Now, the question is that this characterization is very much useful to check the compactness of a set in Rn. Now, the question is a closed and bounded subset of CXRn. Okay, so if we replace y by Rn, so we have the set of all continuous functions from a metric space X to Rn is compact. The question is a closed and bounded subset of CXRn compact? The answer is no. However, a subset of CXRn is compact if and only if it is closed, bounded and equicontinuous. Okay, so a set is equicontinuous. So we have to know the definition of equicontinuity, and such a result, we say that a subset of CXRn is compact if and only if it is closed, bounded and equicontinuous, is known as Arzela-Ascoli theorem. So, the main task of this section is to prove or to establish the Arzela-Ascoli theorem. So, basically, in this section, we will discuss the Arzela-Ascoli theorem, which says that a subset of CXRn is compact if and only if it is closed, bounded and equicontinuous. So, first let us define the equicontinuity of a function. So, before that, we define the point-wise boundedness of a collection of functions. So, let us take X is any set, okay. I am not necessarily a metric space. So, X is any set, the collection B of functions Fn, okay, from X to R. That is to say, the collection of real valued functions on X is said to be pointwise bounded if for every x in X there exists a constant mx, okay, such that mod of f and x is less than mx for all n in its n group. So, here is this m is depending on this x. So, a collection of functions, a collection of real valued functions defined on a set X is said to be the collection. Collection is said to be pointwise bounded if for every X there exists a constant m, and this constant m depending on X such that mod of f and x is less than or equal to mx for all n is natural number n. Now, this collection beta of function fn from X to R is said to be uniformly bounded or simply bounded if there exists a constant m, okay, which such that f and x is less than or equal to n for all natural number n and for all x. It means that this constant m works for all x in M. Okay, then we say that the family of functions the family of real valued functions defined on a set X is uniformly bonded or simply bonded if there exists a constant m such that mod of f n x is less than or equal to m for all natural number n and for all x in x. So that is to say, this capital M independent of x, or you can say that capital M works for every x in M. Okay. Now, we have a remark. We say that in the above definition of pointwise bounded collection of functions, mx depends on the point x. It may vary from point to point. For example, we can consider a collection of functions such that f of x is equal to alpha x for all alpha lies between closed interval 0, 1. Okay, so this is a collection of functions. Now, this collection of functions, so we can take mx. So mx is equal to f of x. So you take mod of m of x is equal to. So here is we can take mod of f of x is equal to mod of alpha x, which is equal to mod of x. So this here is equal to because this function is from R to R, so we can write this. But now this we can choose because this is alpha lies between 0 and 1. So the whole thing, so this is less than or equal to mod of x. But mod of x we can choose our m of x. So whatever is x according to x, we can choose m of x. Okay. So here is this m is depending on x. And so you can see that in this case, the boundedness is pointwise, okay, not uniformly. Now, if X is compact metric space, then the uniform boundedness is same as boundedness in the metric space CXR rho, where rho is defined as usual in this way. So, if X is a compact metric space, then the uniform boundedness, okay, is same as boundedness of the space CXR. That is to say, the boundedness of this space with respect to this metric. Now, the question is that does every uniformly bounded sequence or does every bounded sequence of functions has a convergent subsequence? Every uniformly or bounded sequence of functions has a convergent subsequence? The answer in general, it is not true. You can say no. How? Let us consider one example. So we consider a sequence Fn of continuous functions defined as Fnx is equal to x raised to the power n on the closed interval 0, 1. Then this sequence on the closed interval 0, 1 is uniformly bounded, but has no subsequence that converges uniformly. Although sequence converges pointwise. Okay, so here you can say that this statement, the answer of this statement is no. Now, we will see that if Fn is pointwise bounded, then it is not necessarily uniformly bounded. So, to see that a sequence is pointwise bounded, then it is not necessarily uniformly bounded. So, for that let us take Fn be a sequence of functions in C0, 1 R defined by Fnx is equal to x n raised to the power 3x divided by 1 plus x n raised to the power 4x. Then we see that Fn converges pointwise to the 0 function, that is to say a 0 function f, that is to say the value of the function at every point is 0. So, okay, as Fnx is equal to 0 for at x is equal to 0, and for x is equal to 0, we have this term is less than 1 over nx. Okay, so as for each x, f and x converges, and so it is bounded, and therefore Fn is pointwise bounded. Now, we will see that it is not uniformly bounded. So we can maximize Fn over closed interval 0, 1, and we find the maximum occurs at the critical point x is equal to 1 over n square. And now, since this is the metric on this space C01R is defined in this way, but this is what? This is equal to Fn 1 over n square, and so this is equal to n by 2. And now you can see that as n tends to infinity, this tends to infinity. So this the limit of this is equal to infinity, and therefore the Fn okay does not converge to f. Okay, so or you can say does not converge uniformly. So the sequence Fn is not uniformly bounded. Now we have a proposition which says that if X is a metric space and F is a pointwise bounded family of continuous functions. Pointwise bounded family of continuous functions. Then there exists a non-empty open set G and a constant m such that mod of f of x is less than or equal to m for all f in f and for all x is in G. In other words, you can say that if f is a family of pointwise bounded continuous functions, f from x to r, real valued continuous functions, then because this family of bounded functions, okay, so bounded functions means mod of f of x is less than or equal to m. Okay, and not only this, there exists an open set where and constant m such that mod of f of x is less than or equal to m in the neighborhood of this x. So if this is true for one x, because it is true, because it is bounded, pointwise bounded, so it is true for x. So now we say that it is also true for all the points in the neighborhood of x. To prove this one, let's take for all n natural number and all the functions f in this collection, we see that the f inverse closed interval minus n to n is closed, because minus n to n is closed and f is continuous, so continuous image of closed set is closed, so this is your closed set. And we can set an is equal to the intersection of f inverse closed interval minus 1 to 1, and we are taking the intersection of all f in this family. Okay, and this is your closed set, and arbitrary intersection of closed set is closed, so an is closed. Okay, so this is your closed. Now since f is pointwise bounded, so since f is pointwise bounded, this an, the union of an, union has taken all natural numbers, it is equal to whole r. Okay, this is equal to whole r. So by corollary 3.33, all an cannot be nowhere dense. Okay, and if a and naught is not nowhere dense, then there exists an open set G such that every open sphere inside G contains elements from a and naught. And since a and naught closed, G must be a subset of a and naught. Then by the definition of a and naught, we have the mod of f of x is less than or equal to n naught for all f in capital F and for all x is in G, and that is the proof of the result. Now we have another proposition. We say that let X be a countable set, okay, countable metric space, and Fn be a pointwise bounded sequence of functions Fn, then Fn has a pointwise convergent subsequence. Okay, so if this is your compact, X is your compact, and Fn be a pointwise bounded sequence of functions Fn, then this sequence Fn is pointwise, this sequence has a pointwise convergent subsequence. To prove this pointwise convergence of the sequence, let x1, x2, xn be an enumeration of the elements of X, because X is your countable set. Then the sequence Fn x1, Fn xn, Fn x1, okay, with this x1, so here I am taking x1, Fn x1, this is bounded, and hence we have a subsequence of Fn which we denote by F1k, and k runs from 1 to infinity, such that F1k x1 converges, or is convergent. Next, we can take F1k x2. Now here we took F1 and now we can take F1, and this is again bounded, and so F1k has a subsequence F2k such that this converges. Note that this is still convergent. So in general, we have a sequence Fmk which is a subsequence of this sequence such that this converges for j runs from 1 to m. Let Fm plus 1k be a subsequence of Fmk sequence such that Fm plus 1k xm plus 1 converges, okay, and hence it converges for all xj and j runs from 1 to 1. Okay, rinse and repeat. Then we will see that if X is finite, we are done as the process stops at some point. Now, if X is countably infinite, pick the sequence Fkk. Okay, this is a subsequence of the original sequence Fn. So, for every m, the tail Fkk is a subsequence of Fmk, and hence for any m, the sequence Fkk xm converges. So we have a subsequence. So we can say that Fn has a pointwise convergent subsequence. Okay. Now, as I have mentioned in the beginning of this talk, that we will have to prove, or we will have to discuss to prove the Arzela-Ascoli theorem. We say that every compact subset of CXRN is compact if and only if it is closed, bounded and equicontinuous. So we have to give the definition of the equicontinuity. So let us have the definition of the equicontinuity. So X and Y are two metric spaces. The collection F of functions F, the collection of functions F from a metric space X to another metric space Y is said to be equicontinuous if for every epsilon positive there exists a delta positive, such that for all elements of this collection and all xy in X, dxy is less than delta implies dfx fy is less than epsilon. Okay. Now, this collection, you have a collection of functions. So, collection of functions is called equicontinuous. Okay. So, equicontinuous means, so for all xy, so for every epsilon positive, there exists a delta positive. Okay, such that this implication holds good. It means that this is because the function f is continuous. So f is continuous. So every function in this family is continuous, because If this is hold good, then this is for every function. So this is holds good for every continuous function. So this is the collection of functions f is said to be continuous if and only if for every f. For every f, this epsilon and this delta works. Okay, note that the same delta, okay, works for all x and y as well as for all functions f. So here is this delta works for all f and all x and y. We are not saying that. If you look here is in other way, that suppose this is what? This is the f is the collection of functions. Okay, collection of functions. And now forget about this one. So f is continuous if for every epsilon positive there exists a delta positive such that this is holds good. Okay, but what we are saying? We are saying that the collection of functions is equicontinuous if for every epsilon positive there exists a delta such that for all f, because if we are taking the collection of functions, so say for example you have a function f1, okay, for example suppose you have a function f1 x2y, we have a function, another function x2y. So for every epsilon positive there exists a delta positive such that for all xy, what we dxy is less than delta implies dy dx f of x f of y is less than epsilon. But for the continuity of the f2, this delta may be different. This delta may not work. So we will have for every epsilon 1 is greater, there exists a delta 1 greater than 0 such that this holds good. So here is x as this, then is dxy is less than epsilon 1 implies that dy, here is x, f of x, f of y is less than delta 1. So here is we have delta 1, here we have delta 1, here we have delta. So it means that for each function we have different delta. Okay. So if a single delta will work for all f, okay, if the single alpha works for all f, then the collection of functions is said to be uniformly continuous. So that is a very important thing. Here is you can see here is important. So here is I put the note that the same delta works for all points x and y as well as for all f in f. Now, so there is a very slight difference between the collection of continuous functions and a collection of functions which is known as equicontinuous. Okay. So slight difference in the definition when you have to look very carefully. Okay. Now let us take an example of equicontinuous, the collection of equicontinuous functions, the collection of functions which is equicontinuous. So let R be a metric space with respect to the usual metric and Fn be a sequence of functions which define Fn x is equal to 0 if x is less than n and Fn x is equal to x minus n if x is less than or equal to n. Then this collection of functions is equicontinuous. This collection of functions is equicontinuous. Take another example, okay, of functions, collection of functions which is not equicontinuous. How we can see here? Let's take again R with the usual metric and Fn be a sequence of functions defined on the closed interval 0, 1 as f and x is equal to x raised to the power n for all x in the closed interval 0, 1. Then the collection Fn, okay, the collection Fn is not equicontinuous. Why it is not equicontinuous? Let us see here. Indeed, let xn is equal to, we can take a sequence we can take xn is equal to 1 minus 1 over n, okay, which of course is an element of the closed interval 0, 1. So instead of x, take xn is equal to 1 minus 1 over n, and take yn is equal to 1 in this closed interval. Then we see that xn minus yn, which is equal to 1 over n, and this converges to 0 as n tends to infinity. Also, we can see that fn yn minus fn xn. So it is equal to fn yn. So you apply put x is equal to yn. So yn is equal to 1. So 1 raised to the power n. So it is equal to 1. Now fn xn. So fn xn. So you put x. Okay, x is equal to put 1 minus 1 over n. So 1 minus 1 over n raised to the power n. So it is raised to the power n. And now this converges to 1 minus e raised to the power minus 1 as n tends to infinity. And this is always greater than 0. Okay, so this is greater than 0. So if we take epsilon is greater than 0 such that epsilon is less than 1 minus e raised to the power minus 1. Okay, for instance, we can take epsilon is equal to 1 minus e raised to the power 1 divided by 2. Then there exists a positive integer n such that this is greater than or equal to epsilon for all n is n. So it means that our definition, so in the definition is here is for epsilon, this is less than epsilon does not hold good, and because this is greater than epsilon, and therefore fn is not an equicontinuous collection. So this collection of functions which is defined in this way on the closed interval ab is not equicontinuous collection. Okay, so let us take when we will have a collection of functions which is equicontinuous. So if we consider a family of functions fn on cxy, so cxy is family of continuous functions from a compact space X to R. That is to say, fn is a collection of real valued functions defined on a compact set X. That family, so this sequence converges uniformly, and this sequence converges uniformly, then this family fn is equicontinuous. So equicontinuous, so if you have a sequence, family or sequence of real valued continuous functions defined on a compact set such that it converges uniformly, then the family fn or the sequence fn is equicontinuous. So to prove that equicontinuous, we will have to prove that because here is the image of this for all x lies in R. So we have to prove that the fn x and fn y is less than epsilon. Okay, so let epsilon be given. Then since fn converges uniformly, okay, there exists a positive integer n such that fn x minus f capital N x is less than epsilon by 2 for all n is greater than n and all n is equal. Okay, so this should be n. Sorry. Okay, this is capital. Now, since f1, f2, fn is a finite set of uniformly continuous function and so an equicontinuous family, therefore there exists a delta is greater than 0 such that fjx minus fjy is less than epsilon by 2, which is less than epsilon whenever the distance between x and y is less than delta. Now take n, small n is greater than capital N, then for all x and y, okay, such that dxy is less than delta, we have fn x minus fn y is less than or equal to this plus this plus this, and this each term is less than epsilon y2, so this whole thing is less than or less than epsilon, and therefore the fn is equicontinuous. Okay, now note that a uniform equicontinuous sequence in the metric space CXR is pointwise bounded. That is, pointwise bounded is bounded in CXR, and furthermore, it contains a convergent subsequence in CXR. Now, we present the Arzela-Ascoli theorem about the existence of convergent subsequence. Okay, so this we will discuss in our next talk. Thank you very much.